All right. So welcome to surface group representations and projective structures. And yeah, great pleasure to introduce my comrade in arms and from grad school. He was not supposed to be the speaker. So every 10 years, we seem to be trading this insult back and forth. So I have the real pleasure of introducing Ken Bromberg, currently from Yale, usually from Utah. And he'll be speaking about Schwarzian derivatives.
Hi, great, thanks. Glad to be the first speaker. It's a great pleasure, and it's great to be here. So what I wanted to talk about was, today I'm going to talk mostly about Schwarzian derivatives, and then I think maybe Wednesday, in my second talk, I'll talk about something called Epstein surfaces, and the relationship between the two objects. So maybe I just want to start off, though, by saying what the main objects that we're going to be looking at are, and introduce sort of the basic ideas of the basic objects of what an Epstein surface is, and and then for most of the talk today, I'll focus just on Schwarzian derivatives. Okay, so I want to start off with talking about locally univalent maps. So what this is we take, just say, some domain in C, or maybe the Riemann sphere if you like, and then we take a holomorphic function. This time I definitely want to take it to the whole Riemann sphere. And so F is holomorphic, and the derivative is never zero on omega. Okay, so just by classical theory of holomorphic maps, this means this map is locally injective. And so local univalent is sort of the classical word for a holomorphic locally injective map. So today, mostly we're just going to be talking about this, but let me just say a little bit about three-dimensional hyperbolic geometry. So the Riemann sphere is naturally the boundary of hyperbolic 3 space. Okay? If you think about the Ball model for hyperbolic space, its boundary is a sphere, and we can naturally identify the isometries of hyperbolic space with conformal automorphisms of the Riemann sphere. Right, so we have this identification. Let me write it this way. With conformal automorphisms of the Riemann sphere, this is isomorphic to orientation preserving isometries of the three-dimensional hyperbolic space, and these are both the same as the Lie group, the SL2C. Okay, so this is one natural association between these two objects. So what I'm going to talk on Wednesday about surfaces in hyperbolic space, and the way this is going to come up, well, let's start with a surface in hyperbolic space. So let's take some immersion from the same domain, but now instead of into the Riemann sphere, into hyperbolic space. And what one can do, so this is an immersion, so at every point in the image, there's going to be a normal vector, right? So we'll choose some orientation for omega, and that will give an orientation for the surface. I mean, the orientation for omega naturally comes because this is sitting inside, the domain is sitting inside C. And we can lift to a map from omega to the unit tangent bundle of H3. And all this is doing is that F hat of Z, this is equal to the unit normal of the immersion at the point Z, at F of Z. Now, the nice thing about looking at this immersion, there's a natural sort of one-parameter family of maps one can get out of this. So if we have a vector in hyperbolic space, we can flow along the geodesic. So we can so in particular, we have the geodesic flow. Right, so just draw the picture. So we have some vector, and then we flow forward some time t, and we get another vector. So this is distance t. Okay, and we can compose our lifted map with g of t to get a whole family of maps. And then I can let capital F of t, so this is the projection back down into hyperbolic space, where I is the projection of the unit tangent bundle back to H3 itself. And then what happens is we can take the limit, so we can let f infinity of z be the limit as we go to infinity of these maps. And so the point is, well, what do we have here? So now what is f infinity? F infinity is now a map from omega to the boundary of hyperbolic space, which is the original, which is again the Riemann sphere. So we're back to our original situation where we had a map from a domain in C to the Riemann sphere. Okay, so this is how you get a correspondence between the two things. Now, what will this map look like? So this is really going to depend very strongly on what the curvature of the original immersion. So, for example, if one simple example is when this was just when you just took when omega was, say, a round disk, and this was just an embedding of a two-dimensional hyperbolic plane in hyperbolic 3 space. But we're going to describe a way of building one of these maps out of any. So we're going to start with the local univalent map, and we're going to describe a way of building a map, canonically associating to that a map in hyperbolic space. And we're going to see how the geometry of that map and the geometry of the original univalent map are related. Okay, so that's sort of the goal. Okay. All right, so now I just want to talk about the Schwarzian derivative. Okay, so this is an object that you associate to local univalent maps. So what is this going to do? What is the point of this derivative? So what we want to do is we want to measure, so this is sitting inside the Riemann sphere, and we want to measure how close this map F is to being a Mobius transformation. Okay, and this is, so this Schwarzian derivative is sort of a central tool if you're studying complex projective structures. So I know Shinpei Baba is going to talk about this some more next week. I'm not sure how much the Schwarzian itself will come up. But this is a key tool when studying projective structures. So how do we decide how closely this thing, how closely this thing is to a Mobius transformation? Well, what I want to do is at each point, I want to approximate the map F by a Mobius transformation. So I want to approximate F by a Mobius transformation, an element of PSL2C. In particular, at every point, I'm going to define a map, which I'm going to call MF, from omega to PSL2C. And MF of Z, this is what's called the osculating Mobius transformation. And its definition is just that we have that MF of Z, so this is a Mobius transformation, right? So I can plug in an element of C into this. This is a function on C hat. So in particular, I can plug Z into it. And my definition is of how this is chosen is that when I take this Mobius transformation and I evaluate it at Z, I get F of Z. When I take the complex derivative of this and I evaluate it at C, I get the derivative of f of C. And when I take the second derivative, that should be the second derivative of f at C. And the point here is, well, how many parameters are there in a Mobius transformation? Well, you write AZ plus B over CZ plus D, that's 4 parameters. But then we want to assume, for example, that the determinant is 1, so there's really only 3. So the space of Mobius transformations is a 3 complex parameter space, and here we're picking out 3 parameters, so there's a good hope that we can do this. So there's an exercise to check that this is well defined. You can always do this. For every locally univalent map, and it's key that it's locally univalent, there is a unique Mobius transformation that satisfies these 3 properties. So this gives us a map from our domain, our complex domain, to the Lie group PSL2C. So our goal is to measure how this map differs from being a Mobius transformation. We've at each point given an approximation, the best approximation we can to the map being a Mobius transformation. So all we're going to do is we're going to differentiate it. So we want to differentiate the map MF. Okay. Okay, so what is the derivative going to be? Well, it's going to be a map from the tangent bundle of omega to the tangent bundle of the Lie group PSL2C. And in some sense, this is the Schwarzian derivative. Now, if you've seen the Schwarzian derivative defined before, it's usually just given as some, there's just some equation in terms of f, and it's usually thought of as a function. But this is one way of thinking of what the Schwarzian derivative is. Okay, so maybe we don't want to think about maps between bundles, so we can do 2 things to simplify the picture here. The first is that if we have a domain in C, in the complex plane, every tangent space can be canonically identified with just a copy of C itself. The other thing we can do is, well, what is the tangent space to a Lie group? It's just the Lie algebra. Okay, so every tangent space to the Lie group is just the Lie algebra. Okay? And so we can identify this single space. So this, right, so let me write that down. So for all Z in omega, we have that the tangent space at Z is canonically just C. There's a canonical identification. We also have that the tangent space of PSL2C, this is just canonically identified with the Lie algebra little SL2C. Okay, and so I'm going to use slightly different notation here. So I'm going to use the derivative of M. And this is not to be confused with the derivative I wrote here of the given Mobius transformation, but the derivative of the map M at a point Z. Well, this is going to be the map between tangent bundles applied. Well, the complex vector space C has a canonical basis, and I'm just going to pick this image of this at DDZ. Okay? And this, I want to think of this as a map from omega total SL2C. Okay, so in a minute I'm going to prove a proposition. Let me just write it down for now. And what is this? So what is this object? It's an element of the Lie algebra. So how do I want to think of the Lie algebra? Well, the Lie group is conformal automorphisms of the Riemann sphere. I mean, this Lie group is many things, but one way we can think of it is as conformal automorphisms of the Riemann sphere. So these are maps of the Riemann sphere to itself. Well, what then should the Lie algebra be? Geometrically, we can think of the Lie algebra as infinitesimal conformal automorphisms of the Riemann sphere. In particular, this is vector fields on the Riemann sphere that, when you flow them, give conformal maps. Now, there's a sort of an exercise in complex analysis. Such vector fields are represented by quadratic polynomials. So what this is going to be, this is going to be a vector field, and I'll use W as the parameter. This is a vector field on the Riemann sphere. And what this vector field is, it's going to be given, if you have a vector field on the Riemann sphere that's flow is conformal, this map has to be holomorphic. And in fact, because it's defined in the whole Riemann sphere, it's sort of a exercise in complex analysis, this has to be a quadratic polynomial. And in fact, what the quadratic polynomial is, let me actually write it down this way. So this vector field is going to be a quadratic polynomial. What this quadratic polynomial is going to be, so for every z, we get a new vector field. That vector field is always going to be of the form some constant times the vector field w minus z squared. So remember, in this case, z is, for each z, we're getting a vector field. So on the right-hand side, you should think of z as being fixed. Okay? So when I fix z, this defines a vector field on the Riemann sphere. And this function here this is going to be a holomorphic function. So when we take this derivative, we're going to get this very special vector field. At each point, we'll get this very special vector field in the whole Riemann sphere. And it's basically going to be what this is. This is going to be a vector field with exactly one fixed point. And there's going to be this parameter in front, which is going to depend on z, and it's going to depend holomorphically on z. And over 2. I put dashes through my z's. So. This is the Schwarzian derivative. This is what's classically called the Schwarzian derivative. Okay, so I'm going to come back to this. But before I do that, I'm going to mostly save the discussion of this surface in hyperbolic space until next time. But I want to briefly sort of bring it into the discussion now. And then we'll come back to a more detailed discussion of this proposition. Okay, so I have this map from omega to PSL2C. Now this is two things, right? This is conformal automorphisms of the Riemann sphere, and this is isometries of hyperbolic space. So what we can do to define a map okay, and here this works more generally, but let me just say, let's assume that omega is, say, the unit disk or the upper half plane. And I'm going to draw a picture for the upper half plane, and then you think about how this would work in the unit disk. Okay, so let's first draw hyperbolic space. So let's use the upper half space model of hyperbolic space. So here is C, and then above it lies the upper half space. Here is the real axis sitting inside C, and then here is the upper half plane. Okay, now above the real axis, I have a copy of H2. And I want to define, and now I have some, and I also have some arbitrary point P sitting inside H3. And I want to define this map. I want to define f of P. I'm going to do it as follows. So through the point P, I can find a unique geodesic that, in hyperbolic space, so this geodesic is orthogonal. There's a unique geodesic that goes through P and is orthogonal to this red plane. If you take any two-dimensional plane sitting in hyperbolic space and any point P, you can find a unique geodesic through that point that's orthogonal to the given point. This, because of the particular choice of plane I chose, one of the endpoints of this geodesic will land in the upper half plane at some point z. So the way I'm going to define this point f of p is I'm going to take my osculating Mobius transformation at z, and now instead of thinking of this as a Mobius transformation acting on the Riemann sphere, I think of this as an isometry of hyperbolic space. Okay. So, oops, how did I, wait, the way, I should have looked what I wrote. Okay, so this, the way I actually set it up was not what I intended to do, but it's essentially equivalent. The way I set it up, this is a map from hyperbolic space to itself. Now, if I restrict this map to this plane, I get an immersion of a surface in hyperbolic space. And actually, that's what I intended to do. I was getting a little bit ahead of myself. So maybe I'll write that. Yeah, so maybe I'll. So another way I could have done this is if I wanted to define a. Yeah. Okay, so if I. This is what you get when you put your notes down. So if I wanted to define this, what I meant to initially say is if I take any point z, there is a unique point on this plane, P, such that the geodesic orthogonal to the plane through P has endpoint z in the upper half plane. And then I can define f of z to be, the same thing that I wrote down here. The map is essentially the same, but now I'm just restricting it to this given plane. And I'm thinking of the domain as the original domain omega. So. Okay, now I can repeat that construction that I did over there. And the key thing is that the map that I get when I take the limit is the original map that I started with. And this is an example of something called an Epstein surface. Okay. And so on Wednesday, we'll talk about, how the curvatures of this surface and how that tells you information about the original map. Okay. So let's go back. Are there any questions about that so far? Oh, okay. Yeah. So you take this. I fix this plane sitting inside of hyperbolic 3 space, and for any point on the plane, I have this unique geodesic that's orthogonal to the plane. And that geodesic will hit the upper half plane at some point z. Okay? So now I plug z into my oscillating Mobius transformation. So now I think of this as an isometry of hyperbolic space. And now I apply that isometry to the point P. I keep doing it backwards in my head. I want to start with z, sorry. I want to start with z. I start with the point in the upper half plane. I have the unique point P, where the geodesic through P is orthogonal, and so the domain is omega. Right, so what we can do, right, so I didn't need to just choose this. I could have done this with, instead of choosing this hyperbolic plane P, I could have just chosen any surface I want that had the property that when I flowed, it gave me the upper half plane. I mean, the key property I needed was that for every point z, there was a unique point on the surface where the normal to that surface hit the point z. So any surface that has that property would have worked. And so another example of such surfaces is we can take, instead of this initial plane P, we could rotate this plane by some angle in the Euclidean metric. But in the hyperbolic metric, what you do what that gives you is it gives you the set of points that are some fixed distance d from the original point. So it gives you a constant curvature plane on the surface. Say again? The limit I'm going to take exactly the same as I did before. I'm going to talk about this more on Wednesday, so maybe I should, yeah. So the point is, if you take this map F and you just repeat this construction that I wrote over here to get the limit, you'll get the original map little f back. My initial choice of the plane. Depending on how you, yes, well, but maybe I should just save this for Wednesday. I'm not going to. Yeah. So we'll spend Wednesday talking all about the geometry of these surfaces. This is just supposed to be a little hint. What? Can you say that again? What is M sub f? M sub f is always the same thing. It's this osculating Mobius transformation. Well, if I gave you, I mean, I don't have a concrete map. So if I gave you so there's some examples. I mean, you can write it down pretty explicitly, I suppose, but I'd have to give you the map F to say something concrete. Oh, that's my countdown thing, I guess. I see. All right, great. Okay. So let's return to the discussion here. So how do we take this derivative? All right, so to start with, let's let phi of t be a one parameter family in PSL2C. And assume that phi naught is the identity, just to make life simple. All right, so what do we want to think of as the derivative of this? So when I put a little dot there, if I have some object parameterized by t, I'll think of the dot as this is supposed to be the time zero derivative of this family. So what is this? This is supposed to be, so if I look at the map, so if I fix z, the map t goes to phi t of z is a, say, smooth path, assuming that the phi t are smooth. So I fix z, and then here is phi 0 of z, and then this just traces out a path on the Riemann sphere. Okay, well, this path has a derivative, and this is just the time zero derivative of the path. By definition. Okay, so this is a vector field. Okay, and it's a vector field whose flow is a family of conformal maps. So in particular, what I was saying before is that phi p of z, this is going to be given this will be given by a vector field where we take some function times d dz, where p of z, this is a quadratic polynomial. Okay. Now, what is this? Right, this is just Mobius transformations, right? So I can also write this as, I can write this as you usually write a Mobius transformation. And then I'm just differentiating the quotients, right? To get this vector field, all I'm doing is I'm just differentiating the A, the B, the C, and the D. So more explicitly, I can just write this as the derivative of this expression with respect to t. So when I do that, I get, again, the dot indicates the time zero derivative. I'm going to, unfortunately, hit this line that we cross. Okay, try to squeeze this in. Okay, so maybe I'll just write it down and let you check. So what you get when you do this, you just use the quotient rule. Nothing fancy is going on here. And you use the fact that at time 0, A and D are 1, and B and C are 0. Okay. And indeed, this is exactly a quadratic polynomial, as I predicted, as I said. I mean, but this is a general fact. When you have conformal automorphisms of the Riemann sphere, they're always going to be represented by a quadratic polynomial times d dz. So we can apply that to try and calculate what this derivative of this function mf is. Okay, so, well, first of all, how can I write down what mf is? So at every point, this is a Mobius transformation that depends on some z. So we fix z, we get a Mobius transformation, and we can plug w into that Mobius transformation. Okay, I don't want to write down a formula for the Mobius transformation. I could, but it would be sort of unpleasant. Instead, what I'm going to do is I'm just going to write down the Taylor series for the Mobius transformation. So this is some Mobius transformation, and I know what it looks like. Its two-jet looks like. I know what it looks like. Its first two derivatives. So what does this look like? This is just f prime of z. So I'm going to write the Taylor series of m of z centered at the point z. So the derivative, the first derivative of this, the value of this function at z is just f of z. So that's the first term, or the 0th term maybe. The first derivative of this function at z is just the first derivative of f. And the second derivative is the second derivative at f. And now, I mean, a Mobius transformation, it looks very nice when you write it as a fraction, but if you write it as a Taylor series, it's going to go on forever, typically at least. There's going to be some other coefficients here. Okay, so what I want to do is I want to differentiate this. And I just want to use what I did over there. So I now have, instead of just having a one real parameter family of Mobius transformations, I have a family that's parameterized by the complex plane. But everything in sight is holomorphic, so we know we can just differentiate it like we normally do. The one thing I need to be careful about is that calculation I did over there, I did it with the assumption that where at time 0, that phi of 0 is the identity. So to start with, I'm going to assume, I want to assume that MF of Z, this is just the identity Mobius transformation. And then when I differentiate, and I'm differentiating this with respect to Z. I get some nice cancellations here. So first of all, let's see. So we have f prime of Z. Then the derivative of this, we need to use the product rule. It's going to be the second derivative of Z times W minus Z. Okay, then when I take the derivative of this, again, I'm differentiating with respect to Z. I'm going to get a negative 1 when I differentiate this term. Here we'll have the third derivative. And now I need to differentiate this, and I get a negative. Second derivative. The 2's cancel out. Plus all these other terms here. So this A of n, this depends on Z. So maybe I should write this as a function of Z. I don't know exactly how, and here we're starting from n equals 3 to infinity. So I take the derivative of that function. Who knows what that is? Yes. No. At the point Z, it's equal to the identity. So I'm gonna take the derivative of I'm gonna take the derivative of this at the point Z. Okay. So Z could be 0, I guess, if you wanted, but. Okay, so what do we notice? We notice that lots of things cancel out. Now, we know over here the only terms that we should only have terms that are there should be no terms that are above quadratic. All right, so the only term in here, right? So we're starting here at n equals 3. The only term in here that's going to be quadratic is this right-hand term here when n is equal to exactly to 3. All the other terms will cancel out. They have to. You don't need to know exactly what they are. So there'll just be one term here with 3a3 w minus z squared. Okay, but what is a3 at z? This is just the Taylor series. This is just the third term in the Taylor series for the identity. So at z, this is 0. So note that at the given z, I see, I didn't. Here, let me put a z naught in here. Maybe this will make it slightly less confusing. Okay, so we take this derivative, all these terms cancels out, and then we plug in our given z naught. So we're differentiating with respect to z, so z is varying, and then we plug in our given z naught, and then everything cancels out except for this term. Okay, and this makes sense, right? You know, we've we've approximated this thing to up to the quadratic term, so the difference is going to be in the third derivative. Okay, so that proves this, at least it proves this part of the theorem at least when this Mobius transformation is the identity at a given point. Okay, so what do we do? So this calculation won't work if we at least not as simply, if we assume, if we don't know that at the given point we're taking the derivative, that the oscillating Mobius transformation is the identity. I mean, what happens over here if we get rid of this assumption? So what happens is you see that we can do the same thing we did before. We can take this path, we can take the time zero derivative, but if phi naught is not the identity, so when phi naught is the identity, this is equal to z. If it's not the identity, this is just some arbitrary point. Okay, so this equation defines a vector field, but it doesn't, so really the way the vector field, okay, the base point of the vector is not at z, it's at phi naught of z. Now, how can we get around this? Well, I'm not going to change the vector field itself. So I can replace phi of t with phi naught inverse composed with phi of t. Okay. So the vector field will be the same when I do this, right? But now I see that at t equals 0, this is the identity. So if, say I let this be my new path, then I can do the same trick. And now I get a vector field, just like I did before. So what is happening here? So if you think about what is the Lie algebra here? So this is the set of left invariant vector fields on the tangent space. So if you're not at the identity, what do? You need to take, if you're not at the identity, there's a unique vector field, which if you do left translation, will get you, there's a unique vector that will get you to the new vector. So we're just using the left invariance of the vector fields here. So what I can do here is, in particular, I'm going to let phi equal the inverse of this Mobius transformation. And the point is that if I look at this derivative of this oscillating Mobius transformation map, these two things are equal. In fact, these are equal for all phi in the Lie group PSL2C. Okay, so if I want to calculate the derivative of this map M at Z naught, well, that's equivalent to calculating the derivative of M for phi composed with F. Okay, now what do I need to do here? So here I just need to take the third derivative of this function. Now I'm not going to do that. I do like to do these kind of calculations, but I have some restraint. So here's the little lemma. And it says if phi is equal okay, so this oscillating Mobius transformation isn't the identity, so we take its inverse. Well, then what we want to do is we want to take the third derivative of phi composed with f. Okay, it's a complicated formula. I'll write it this way. Okay, so I'm not going to go through this, how you do this. It's not super hard. I mean, the key thing to keep in mind is what do we know about phi composed with f? So phi is the inverse of this oscillating Mobius transformation. In particular, phi is like the inverse of f up to second order. So phi composed with f looks like the identity up to second order. So what do we know? We know that, so for example, phi composed with f at z naught, this equals z naught. The derivative of this at z naught, this is 1. The second derivative of this at z naught is 0. Right. Up to second order, this is the identity at z naught. Okay, what we want to calculate is the third derivative. Now, when you calculate the third derivative, it's going to be a complicated formula. And what you do is you reduce that complicated formula to something simpler using these facts plus one other fact. So there's something nice about Mobius transformations. So the third little fact you need to use is if you have any Mobius transformation, you can write its third derivative as 3/2 its second derivative squared divided by its first derivative. I mean, this is an easy thing to check, but you combine these four facts, you write down the third derivative, and you get that formula. And it's a complicated formula, so something funny is, you're going to have to do something mildly complicated to come up with it. But that proves the proposition, right? Because this is the Schwarzian derivative. This is a holomorphic function. Notice that our assumption is that our map's locally univalent. So this derivative is never 0. And, by this equality here, we see that the derivative here, well, this calculation worked if this oscillating Mobius transformation was the identity. But we can always make that so by just post-composing with this element of PSL2C, this Mobius transformation. We get the same derivative, but now we can write down the formula here. So now instead of an f here, we have the third derivative of phi composed with f. And we've just seen what that is. That's the Schwarzian. Okay, so there's a general composition rule for the Schwarzian that also can be derived from this viewpoint as looking at it as an oscillating Mobius transformation. So how do we calculate? The next thing I'd like to look at is we want to calculate okay. So, I mean, one can just do it. I gave you a formula, and you can do, you know, for the second thing, you can certainly just plug into this formula and see what you get. Now, that doesn't seem like too much fun. So let's try and think about this in a slightly more clever way. So, the first thing we want to note is that if I take the composition of the oscillating Mobius transformation map M, so what do I get when I compose two functions? So these are two homomorphic functions, and their domains match up in the correct way so that this makes sense. So if I want to evaluate this at a point C, this is just what you might think it is. So this is going to be, well, we take the oscillating Mobius transformation. It's like a chain rule. For G, evaluated at f of Z, and we compose that with the oscillating Mobius transformation for f at Z. Okay, so I want to differentiate this map. So let's think about, I want to think about this map as a composition. I mean, I just want to apply the chain rule. Right? So how can I think of this map? So it's a map from Z to PSL2C, but I can really factor it through a few different maps. So I'm going to compose this as how many? I think 3 maps here. So let's see. So we want to write MGF as a composition of 3 maps. And each individual map we'll be able to take the derivative of, and then we'll apply the chain rule. Okay, so what's the first map going to be? So it's going to be a map from omega to the domain of omega across PSL2C. Now, I told you I'm only assuming that my map is locally univalent. Okay, so this might not really make sense, but we're taking a derivative, right? So when we take a derivative, we only really care what's happening locally. So we can assume that this map is, you know, we can restrict it to a domain where it's actually globally univalent, where it's an injective map. And what's the map going to be here? So the map is just going to be what you might think okay, and then what is the derivative? So on the level of derivatives, well, this is just going to be f prime of z times, it's going to take the vector ddz to f prime of z times ddz, and then this, by definition, is just the m prime. Yeah, that's the first map we want to look at. The second map, its domain is going to be here. And the image is just going to be the product of 2 copies of PSL2C. And so I'm going to take a Z and a phi. Now I'm going to apply G. And then I'm just going to take the phi to itself. And we'll see why in a second. Okay, what does this one do on the level of derivatives? So I take my standard basis element for the tangent space, right? This is just something sitting inside the complex plane. So I take my standard basis element ddz. Here I want to take the derivative of this. This is going to be some element v. So v is going to be some vector field on the Riemann sphere, which I denote v. And here the derivative, again, is easy to take. The first coordinate, the two coordinates are completely independent of each other. And the second coordinate is just the identity, so v is going to go to v. Okay, so the third map, I'm going to have the domain, the product of PSL2C with itself. I'm just going to go to PSL2C. So I take some psi and phi, I'm just going to compose them. Now if I take, now I have two vector fields. I want to look at the tangent map. So this is like a product rule, right? So what do we get? I'm taking the derivative. These are both sitting. This is sitting inside the tangent space of phi. This one is sitting inside the tangent space. Wait, that one's C. This one's phi. And this is an exercise. What you get here is you get the pullback of v by phi plus w. So this is a good exercise in theory of Lie groups. I mean, you can actually prove the usual product rule for differentiation using something similar to this, right? So you can, you want to multiply two functions together, you can think of them as, you can compose them as a map to R2 and then the multiplication map of R2 to R. Okay, so if we follow, our noses through here, the composition of these three maps gives us the map, gives us this map. Right, so we start at omega, and we end at PSL2C. So at least the domain and image are right. But it's not hard to check, right? This is just a fancy way of writing down this formula. So what's the derivative? Okay, so how do we take the derivative? We're supposed to take the derivative of this, what we're supposed to do is we're supposed to take by definition, we take the vector ddz and we see where it goes. All right? So ddz goes to f prime ddz. So here we have f prime ddz, so we instead of having a ddz here, we have an f prime ddz. Okay, so this term is going to become the derivative. Okay, now when we go from here to here, well, what? I have to write it. Oh, this is f, sorry. Did I switch? Oh boy, see? Okay. Wait, where did I switch it? just here. There I did okay. Okay, so this is still correct. Yes. Okay. Okay, so according to this last formula, what I need to do is, so what am I plugging in here? So I see. Okay. I have to, okay, so here we have the DDZ. This becomes F prime. I'm totally confused if I did the F and G's messed up in my thing. Did I do them? Does that look right, Mahan? Did I mess up the F and G? I think I did this correctly. Okay, so what's happening here, right? This is the last step, right? So we had the wait, okay. I think this. I tried to write this very carefully, but I think I messed up the F and G's. So maybe let's just, how much time do we have? Okay, so let me write this out a little bit more carefully. Okay, so we want to see where DDZ goes. So let's follow this composition and see where it goes. So after the first map, DDZ goes to F prime DDZ, and then the other term is MF prime of Z. Okay, now we want to apply the second map. So the term on the left is F prime DDZ. The term on the right is this M prime of F. Okay, so this becomes, right, so we know what happens to DDZ. It goes to M prime G. But now we need to put an F prime of Z in front of it, right? I mean, the map is linear. And then this just becomes M prime F of Z. Okay, so now finally, we want to take this third derivative. What are the 2 points here, right? So the if we follow the maps themselves, right? Yeah, I should have written this both down. Right, so we have Z goes to F of Z. Okay, so what my formula here tells me I need to do is I need to take this plus the term on the right. Okay, so this is the composition rule. Now, what are these various things, right? This is the Schwarzian at f over 2 times w minus z squared dw. What is this? This is, I can pull the f prime out. This is the Schwarzian of G at, did I lose? Like I lost some term here. Yeah, this should be an f of z. Okay, so the last little fact that we need here, so here is a lemma that this term is equal to f prime of z times w. All right, so when you write this all out, what this becomes is we get the Schwarzian of G evaluated f of z over 2, and then there's this, there are two f primes here. There's one here and there's one here, plus the Schwarzian of f at z over 2, all times w minus z squared dw. All right, so the numerator here gives us the composition rule for the Schwarzian. So the conclusion is that we get the Schwarzian of f of g at z. This is the, I keep switching these around. I don't know why I put G first, because it's obviously second in the alphabet, and that is really not a good choice on my part. But so you take the Schwarzian of G, you evaluate it at f, and then the interesting thing here is you take the derivative of f and you square it. Okay, so this is the composition rule. That's the Schwarzian, yes. So we saw actually what happens in what, so if G is a Mobius transformation, what happens? This term, what is the Schwarzian of a Mobius transformation? Well, in that case, the oscillating Mobius transformation map is constant. So the derivative is 0. So if G is in PSL2C, this implies that SG is identically 0, and this implies that, and we already saw this, is just equal to the Schwarzian of F. If F in PSL2 is in PSL2C, well then the Schwarzian of F is 0. Well, then the formula is not as nice. Okay, so here we get this term is 0, right? But we have this funny, the derivative of f squared sitting in here. Okay, so if our univalent map was, say, the developing map of a projective structure, something which Shinpei will talk about next week, then what we'd see, the Schwarzian derivative is not a function on the quotient Riemann surface, but it's a quadratic differential. That's what that f prime squared is all about. Oh boy. Okay. So the natural way to define a norm on the Schwarzian. And, well, what might you do? It's a function. You might just want to take its absolute value. But unfortunately, that doesn't behave well under this transformation rule. So we want to do something that makes it behave well under the transformation rule. So now assume that f, the domain is either the unit disk or the upper half plane. And I want a norm that is invariant under the hyperbolic metric. Rho delta or rho u. So there's natural hyperbolic metrics on both of these spaces. And what are the isometries, the hyperbolic isometries of these two copies of the hyperbolic plane? They're both just Mobius transformations. They're a subgroup of the group PSL2C, right? In the case of the upper half plane, it's just the subgroup PSL2R. For delta, it's conjugate to PSL2R, but it's slightly more complicated to write down what the specific group is. Okay, but in particular, it will satisfy this formula. And so the key is we define the norm of the Schwarzian, which I'll use the 2 bars. Well, we just take the absolute value, and then we divide, so by the metric, squared. So this is the line element, this is an area element. And then the point is that SF of Z, this norm, the Schwarzian at Z, is equal to the Schwarzian of F composed with phi at phi inverse of Z if phi is an isometry of the hyperbolic plane, where we're identifying the plane with either the disk model or the upper half space model or any model you want where the underlying domain is a round disk. Okay, so what I'd like to finish up with, and I'm not going to have time because I spent so much time with that silly formula, is a classical theorem of Nahari and Krauss. Right. So that's what I'm going to do next. So this is the pointwise norm. At any given point, you can define a norm of the Schwarzian by this formula. And then, okay, when you have a norm on a function, you could take the supremum and you get an L infinity norm. So the theorem of Nahari and Krauss, let's say it in the case of if F is globally univalent, then the L infinity norm of the Schwarzian, in particular the pointwise norm of the Schwarzian, is everywhere less than 3/2. So this was originally proved by Krauss, and then it was reproved by Nahari. The proof is not very hard. It is going to definitely take me longer than 55 seconds. But let me just say quickly what you do. So how do you use the fact that this map is globally univalent? So first of all, I'm going to do a little trick. I'm going to rewrite this as f of z over 1 over z. Whoops, over z. Okay, what is this doing? Well, I have some map of the disk. Okay. I also, let's assume, I want to calculate S f of z, and I'm going to assume that z equals 0 and f prime of 0 is 1, and the second derivative of 0 is 0. I can assume that, using my rules over here, I can assume that, there's my time, I can assume that my one jet at the identity is my one jet at 0 is the identity. So what is the point of this construction? Of flipping it over like this? So what this does, and I'll stop in a second, is this maps the disk to some region that contains infinity. So what does the fact that this map is univalent tell us? The fact that this is univalent tells us that this complementary region has non-negative area. This map is not overlapping itself in any weird way. Right? We can estimate the area of this region, and it will always be non-negative. And this is something called the Bieberbach area theorem. And you can use that to bound the coefficients of this function g. And it's not very hard. And the coefficients of this function g, you really only want to know, the coefficients of the Taylor series of this function g, or the Maclaurin series, or whatever you call it. I don't know, anyhow. You can bound the coefficients, and you just want to bound one of them. There's a coefficient here that exactly corresponds to the Schwarzian here. And it's a fun little calculation, but unfortunately I don't have time. Okay, sorry, I'll stop there.